In a mini refinery system on the roof of ETH's machine laboratory, liquid fuel is produced from nothing but sunlight and ambient air. The process chain incorporates 3 thermochemical conversion processes: the capture of CO2 and water from air, solar splitting, and subsequent liquefaction. CO2 and water are extracted directly from the air in an adsorption-desorption process. Both are then fed into the solar reactor at the focus of a parabolic concentrator. The solar radiation is concentrated by a factor of 3000, generating heat at a temperature of 1500 degrees Celsius inside the solar reactor. The heart of the reactor is a ceramic structure made of cerium oxide. Here, a 2-step thermochemical reaction takes place. In the first step, cerium oxide is reduced and oxygen is released. In the second step, CO2 and water are added to produce syngas, a mixture of hydrogen and carbon monoxide. The cerium oxide absorbs oxygen and oxidizes. The initial state is restored and the cycle can begin again. Only the first step of the reaction requires an input of solar radiation. 2 solar reactors are therefore operated in parallel, and the concentrated sunlight is directed at each one alternately. This ensures optimum use of sunlight and improves efficiency. Depending on the method used, syngas can be converted into numerous different hydrocarbons, into kerosene, gasoline, methanol, or other liquid fuels. These are carbon neutral because the combustion releases only as much CO2 as was removed from the air for their production. The entire process chain has been demonstrated under real field conditions. This demonstration represents a milestone in the production of carbon-neutral synthetic fuels, which could play a particularly important role in sustainable aviation.